An engine's compression ratio can be a guide to the power it can generate. It's not always obvious whether one engine is bigger than the other. The size of the engine block can be misleading. Two blocks can be the same size, but one has cylinders bored out to larger volumes. The standard measure of size is called displacement. Displacement is the volume a piston displaces in the cylinder as it moves from its lowest point, or bottom dead center, to its highest point, top dead center. This is also called swept volume. Notice that displacement does not include the volume above top dead center. Engine size is then the sum of the displacements of all the cylinders of the engine. It is called total engine displacement. For this engine, it is 2 litres. Another guide to engine power is compression ratio. It compares two volumes in the cylinder. One is swept volume plus clearance volume. That's the volume above top dead center. The other is the clearance volume only. Putting these volumes into a ratio gives us the compression ratio, 6:1. The larger the first volume and the smaller the second, the higher the engine's compression ratio and the more powerful the engine. To see how valve timing works in a 4-stroke engine cycle, let's show piston motion as a circle. In this simple cycle, each stroke is shown as a semicircle. This intake valve opens at top dead center and closes at bottom dead center. The blue line shows that period and it matches the intake stroke. The exhaust valve opens at bottom dead center, then closes at top dead center before the new air-fuel mixture enters the cylinder. In practice, the intake valve usually opens earlier than top dead center and stays open a little past bottom dead center. The exhaust valve opens a little before bottom dead center and stays open a little past top dead center. When the valves actually open and close can be measured by angles. To make these angles easier to read, let's use a spiral instead of a circle. This intake valve opens 12 degrees before the piston reaches top dead center, and it closes 40 degrees after bottom dead center. The exhaust valve opens 47 degrees before bottom dead center and stays open until 21 degrees past top dead center. This gives exhaust gases more time to leave. By the time the piston is at 47 degrees before bottom dead center on the power stroke, combustion pressures have dropped considerably and little power is lost by letting the exhaust gases have more time to exit. When an intake valve opens before top dead center and the exhaust valve opens before bottom dead center, it is called lead. When an intake valve closes after bottom dead center and the exhaust valve closes after top dead center, it is called lag. On the exhaust stroke, the intake and exhaust valve are open at the same time for a few degrees around top dead center. This is called valve overlap. On this engine, it is 33 degrees. Different engines use different timings. Manufacturer specifications contain the exact information.
This section examines valves. Petrol engines must control the flow of combustible mixture they take in and when it goes in. In small 2-stroke petrol engines, this is done by ports that are opened and closed by the piston skirt during the engine cycle, or by pressure-operated reed valves. Diesel engines are different. Their power and speeds are controlled by the amount of fuel injected, so it isn't necessary to control airflow into the intake manifold. Almost all four-stroke petrol and diesel engines use valves, which are located in the cylinder head. This is also true for two-stroke diesel engines that are used in road vehicles. Valves experience enormous stress even in normal conditions. In a four-cylinder car driven at around 90 kilometres per hour, each valve opens and closes about 30 times a second. Exhaust valves withstand huge temperatures and they can become red hot. A valve must not soften at high temperatures. It needs good hot strength to stand up to being forced against the seat and to prevent tensile failure in the stem. It needs good fatigue properties to overcome cracking. Various surface treatments are used to help the valve resist wear, burning and corrosion. Inlet valves are made of steels mixed with chromium or silicon to make them more resistant to corrosion, and manganese and nickel to improve their strength. Exhaust valves are made of nickel-based alloys. Some high-performance applications use especially hard-wearing titanium alloys. This is a poppet or mushroom valve. It has two main parts, a stem and a head. It fits into a port in the head. Its face makes a gas-tight seal against the seat. During operation, the head near the face of the valve transfers heat to the seat. Some is conducted up into the valve stem. The stem transfers heat on to the guide, so the stem is the valve's coolest part. The valve seat and guide are also cooled by coolant in passages around the valve ports. When a valve does not seat properly, there's a smaller area where heat transfer can occur. That means the face will overheat. Local hot spots can reach such extreme temperatures that the edge of the valve can actually burn. The width of the valve seat is important. A narrow seat is desirable because a thin circular contact with the valve face forms an efficient seal. But a wider seat is better for transferring heat from the valve to the cylinder head. A common compromise is for the inlet valve to have a narrower seat than the exhaust valve. In some cast iron cylinder heads, the seats are cut directly into the edge of the valve port. These valve seat areas are machined from the metal of the cylinder head. In some engines, the valve seat area is hardened during manufacture. In others, hard metal valve seat inserts are pressed into the machined holes. Valve seat inserts are metal rings that match the shape of the valve. They're usually made of an iron alloy. They're used in aluminium cylinder heads to provide a sealing surface for seating the valve. Leaded fuels leave a deposit on the valve that protects the valve seat. With unleaded petrol, however, this deposit doesn't occur, and all cast iron heads used with unleaded petrol have hardened valve seats. The faces of the valve are ground at an angle of 45 degrees or 30 degrees. Some engines use 30 degrees or 45 degree face angles for inlet valves and 45 degrees for exhaust valves. Valve seats are often ground to the same angle as the valve face, but they can differ. The difference is called an interference angle. An interference angle allows for a quick bedding in of the valve face to the seat on new engines. It may also allow for slight changes in angle as a valve heats and expands. As the valve opens and closes, it has a natural tendency to rotate very gradually, so that it keeps seating in a new place. This produces a slight wiping action, which helps keep the face and seat free of carbon. It also helps prevent sticking in the valve guide and distributes heat around the valve seat. On some diesels, the inlet valve has a shroud or mask on the back of the valve head. This is designed to cause turbulence in the incoming air. The position of this mask is critical for best operation, so the valve is pinned to prevent it rotating. If the rocker arm is slightly offset to the valve stem, it can help this rotation. Some engines even use positive valve rotators. The valve operates in a valve guide, and it's exactly concentric with the valve seat. The valve guide is the hollow cylindrical part in which the valve stem moves. The valve guide area can be machined from the metal of the cylinder head, or holes can be drilled for pressed-in guides. Cast iron guides are necessary in aluminium alloy heads to provide a suitable bearing surface for the valve stem. Many heads use replaceable valve guides that are a form of metal bush pressed into holes in the cylinder head. Other cylinder heads have guides cast as part of the cylinder head, then bored to the size of the valve stem during manufacture. In the port and on the valve head. Umbrella seals shed the oil and keep it away from the end of the valve guide. Worn seals or guides, or too much valve guide clearance, will let oil pass the intake valve. The inlet valve is more likely to pass oil through its guide than the exhaust valve. This is because of the low pressure in the inlet port that draws in the oil. The exhaust valve can still have problems because of exhaust pulsing. This creates a low pressure area behind the gases, which can cause oil to pass down the valve guide. Some engines, however, don't use oil seals on their exhaust valves. Valves are normally held on their seats by 1 or 2 coil springs that are compressed between the cylinder head and a retainer on the valve stem. The spring retainer is held on the end of the valve stem by conical-shaped collets. Collets are also known as cotters, keepers, or keys. The springs usually have their coils closer at the bottom than the top. This makes different parts of the spring vibrate at different frequencies and prevents wasteful valve spring vibration. They can also be made of wire with a specially shaped strong section that limits valve bounce. Unless the valve is held on its seat, it also allows leakage from the combustion chamber. Carbon builds up on the valve stem. Intake valves pass only air or air-fuel mixture, so they run at much lower temperatures than exhaust valves. They're usually larger than exhaust valves because the pressure forcing the charge into the cylinder is much lower than the pressure forcing the exhaust gases out of the cylinder. Exhaust gases under pressure need much less space. Different engines use different valve combinations. Having more than one inlet valve provides better breathing. An additional inlet valve allows larger inlet passages and a freer flow into the cylinder, so the engine receives a better charge. Similarly, two exhaust valves mean the cylinder can be designed with larger exhaust ports, which provides a freer flow of exhaust gases out of the cylinder. This section examines valve trains. The valve train includes all of the components that are driven from the camshaft to the top of the valves. There are different types of valve trains, depending on how many camshafts there are and where they're located. This is an overhead valve or pushrod system. The valves are in the cylinder head, but the camshaft is in the block near the crankshaft. A valve lifter or tappet rides on the cam. As the cam lobe reaches the lifter, it rises and transfers the motion to the pushrod. This then moves a rocker, which in turn pushes the valve open. There are different kinds of lifters. A solid lifter is usually a hollow cast iron cylinder mounted in a bore in the crankcase. It's free to rotate slowly, which distributes wear from the cam over the face of the lifter. The gap between the valve tip and the valve train is called valve clearance or valve lash. This must be maintained when the cam is not applying pressure to open the valve. It can be adjusted with a screw and lock nut built into the rocker arm. These adjustments are needed regularly. Many engines now use hydraulic valve lifters. Their purpose is to make the engine quieter and eliminate the need for valve clearance adjustment. When the engine is operating, oil under pressure from the engine's lubrication system is supplied to the lifter. The oil is assisted by spring tension to maintain zero valve clearance, but through a system of valves, it's trapped in the lifter as the camshaft lifts it. Since oil is not compressible, the lifter acts like a solid lifter. When the valve is closed, any oil lost during the previous lift is replaced, and zero valve clearance is maintained. Rocker arms transfer motion to the valves. The rocker arm rocks up and down using a pivot mechanism. Some rocker arms are made of cast steel or aluminium alloy. Others are a steel pressing. Hydraulic valve lifters usually use stamped or pressed sheet metal or cast aluminium rocker arms. In modern engines, the pushrod system is being replaced by the simpler overhead camshaft arrangement. The overhead camshaft is located in the cylinder head. There can be one or two camshafts. Let's look at a single overhead camshaft arrangement. Single overhead camshafts can use rocker arms. The cam can lift one end of the rocker arm, or it can press down on the rocker arm. On double overhead camshaft systems, the most common arrangement is to use a bucket tappet or lifter. It operates in a guide that protects the valve against side thrusts, which it would receive if the cam operated directly against the valve. The adjustment of valve clearance is usually done by changing accurately machined spacers. Spacers are available in a range of thicknesses, and they're exchanged to obtain the correct clearance. Some overhead cam engines use a hydraulic lash adjuster to reduce lash in the valve train. They have zero clearance at the valve stem, so there's no need for tappet adjustment. It can be put in the valve end of the rocker arm. Like the hydraulic valve lifter, it has a body with plunger held against the valve stem by a spring. Oil supplied to the adjuster keeps the plunger in contact with the valve and eliminates lash. Lash adjusters can be put in the cylinder head at the end of the rocker arm. The lash adjusters are stationary and have a pivot for the end of the rocker arm. The plunger in the adjuster holds the rocker up against the cam. In the lash adjuster inside the bucket tappet, the plunger's hydraulic action holds the bucket body against the cam on the camshaft and also against the tip of the valve stem so that there is zero clearance. This section examines camshafts and drives. The position of the camshaft depends on the design of the engine. It can be in the engine block, close to the crankshaft. This is called a pushrod or overhead valve system. Or there can be one or two camshafts mounted in the cylinder head. But in both designs, it does much the same job, driving the valves and the distributor, and sometimes the fuel pump and the oil pump. The camshaft is made of hardenable iron alloy or steel, and it can be cast or machined. The cam lobes are ground to the proper shape and position in relation to one another. Accuracy is crucial. If the cam is not exactly the required shape, or if it becomes worn, there can be impacts, fast valve wear, or noisy operation. The bearing surfaces on the camshaft are ground smooth, and the distributor drive gear is machined into the shaft. The cam lobes are then flame or induction hardened. The camshaft has a cam for each valve. In some cases there is an additional cam known as an eccentric to operate the fuel pump. A gear on the camshaft drives the ignition distributor and often an oil pump. The cam lobe performs three jobs. It opens a valve at the proper time and gives it proper lift. It lets it stay open for a sufficient time. Then it lets it close at the proper time. Accurate valve timing is crucial. Valve timing can vary from engine to engine, as set out in manufacturer's specifications in the valve timing diagram. The shape of the cam is called the cam profile or contour. With the valve lifter resting on the base circle, shown as A, the valve is fully closed, and there is clearance between the rocker arm and the valve stem. The cam rotates. The nose of the cam, B, reaches the valve lifter, and the valve is fully open. The closing flank, C, closes the valve gradually so that it doesn't pound against its seat. On engines without valve lash adjusters, a quietening ramp is built into the shape of the cam. This makes for quieter operation during the opening of the valve. The shape of the nose determines how long it stays open. The camshaft must always be synchronized to run in time with the crankshaft. This can be done by gears, chains, or toothed timing belts. Gear drives are most common in engines with the camshaft in the cylinder block, and in heavy-duty diesels. Timing belts and chains are used on overhead camshaft engines because the camshaft is further from the crankshaft. This is a typical chain drive system. It uses a hydraulic tensioner which is fed by oil under pressure from the lubrication system. The chain also uses guides to reduce noise and vibration. The toothed timing belt is made of fiberglass or wire-reinforced synthetic rubber. Its teeth match those on the crankshaft and camshaft pulleys. Timing belts are quieter than chains, but usually require regular manual tensioning. They also have a shorter life than chains. They need regular replacing around 80,000 to 100,000 kilometres. If a belt breaks, it's not only inconvenient, but on some engines it can cause a lot of damage. This section examines the piston. The piston, with its connecting rod and bearing, transfers the force of the combustion and expansion of the power stroke to the crankshaft. The piston itself, its rings and the piston or gudgeon pin are together called the piston assembly. The cutaway shape on this piston allows it to clear the counterweights on this rotating crankshaft. The shape of the piston crown depends on the shape of its combustion chamber and its compression ratio. The piston crown may be flat, concave, dome or recessed. In diesel engines, the combustion chamber may be formed totally or in part in the piston crown, depending on the method of injection, so they use pistons with different shapes. The piston must stand up to great heat and pressure. It must also change direction from about 10 times a second up to hundreds of times a second. In most engines, the weight of the pistons is important for engine balance. This is why pistons should only be replaced in matched sets. Some pistons are forged, while others are cast aluminium alloys. All pistons expand as they heat up. As there is more metal near the gudgeon pin, this area tends to expand the most. To allow for this, many pistons are machined into a slightly oval shape. This is called cam grinding. Then, as the piston heats up and expands, it becomes round. Other methods to control expansion include steel struts or ribs, expansion slots in the skirt, or slots called heat dams that restrict movement of the heat. This section examines piston rings. Piston rings keep a tight seal within the cylinder to stop the heat and pressure in there from escaping. They also stop oil passing up into the combustion chamber. New rings and cylinders have minor irregularities, and when these wear off, the rings will make a better fit. To help this along, the rings can be given a porous coating. It's softer and wears more quickly than the ring material, which is usually cast iron. To prevent wear, the face of the piston ring can be coated with a harder material like chromium that operates well against cast iron without scuffing. They are split so they can be fitted into grooves in the piston and to expand against the cylinder walls. When they're removed, their diameter's larger than the pistons, so when they're installed, they're compressed and the gap is almost closed. Tension in the rings keeps them against the walls. There are two main types of piston rings: compression rings and oil rings. Compression rings must seal against compression loss during the compression stroke, or the air-fuel mixture won't be fully compressed. They must also seal properly during the power stroke, or combustion gases are forced past the piston into the crankcase. This is called blow-by. A plain compression ring has a rectangular section. It's held against the walls by combustion pressure behind the rings. A tapered ring seals against pressure too, but its slightly tapered face helps scrape oil off the walls as well. Faced rings are designed to better resist heat and wear. A ring that's chamfered or grooved exerts increased pressure against the walls. It's also called a torsional ring. Its shape creates internal forces in the ring so that when it's installed it twists slightly upwards. During intake, the ring scrapes surplus oil off the walls. During compression, they tend to slide over the oil and not carry it into the combustion chamber. In the power stroke, combustion pressure forces down on the top of the ring and also against its back. This straightens it so that it has full face contact with the cylinder walls for effective sealing. Oil control rings prevent excessive oil working up into the combustion chambers. It can be a one-piece ring that depends on its own tension to hold it against the cylinder walls. Slots in the ring and holes in the piston behind the ring let oil return to the sump. Many oil rings are segmental types with 3 or 4 segments. They have 2 side rails and an expander, which also acts as a spacer for the rails. They depend on the expander to hold them against the walls. The expander is made of thin steel with a series of crimps to give it an outward spring force. This section examines the connecting rod. The connecting rod connects the piston to the crankshaft. It's fastened to the piston at its little end by a piston pin, also known as a gudgeon pin. In some engines, the pin is a press fit in the small end of the connecting rod. In others, it's clamped to the connecting rod with a clamping bolt. Another method lets the pin float in both the piston and connecting rod, and it's held with circlips. There's a bearing in the small end of the connecting rod. The big end of the connecting rod has a detachable cap and carries 2 halves of the big end bearing. The big end is attached to the crankshaft at the crank pin journal. Connecting rods must be very strong and rigid and as light as possible. They're subject to stretching, compressing and bending, so they're highly stressed. They're cast or forged to form an H near the small end and an I near the big end. This shape provides greater strength to resist the stresses than a solid rod of the same mass. To maintain engine balance, all the connecting rods in an engine are a matched set. This section examines the crankshaft. The crankshaft is attached to the connecting rod in offset areas called throws, where the downward power pulses change into rotating motion. Crankshafts must be strong enough to do this without bending or twisting. They are a one-piece casting or forging of heat-treated alloy steel of great mechanical strength. Counterweights are formed to balance the throws and also the big end of the connecting rod. Fine balancing is done by drilling out or adding small weights. The crankshaft rotates in the engine on journals, which run in bearings called the main bearings. The connecting rod, with its big end bearings, is attached to the crankshaft crank pins located on the throws. Drilled passages carry lubricant under pressure from the main bearings to the adjacent big end bearings. The rear of the crankshaft is drilled and tapped for flywheel attachment. Near the front of the crankshaft, a timing gear or sprocket is attached to drive the camshafts. A drive pulley is mounted on the front of the crankshaft. It drives many components, including the alternator, the fan and water pump, and power steering. Many inline and V engines have a harmonic balancer attached to the crankshaft. The harmonic balancer is more correctly called the crankshaft torsional vibration damper. It prevents crankshaft vibration. In most cases, the harmonic balancer incorporates the drive pulley. This section examines engine bearings. No engine can run without bearings. Bearings are used in engines to support and protect rotating parts and allow them to turn freely. The connecting rod must be able to spin freely on the crankshaft. The crankshaft must be able to spin freely in the engine block. Connecting rod bearings and the crankshaft main bearings are called split sleeve types, which means that they're in two halves called inserts, slippers or shells. These precision inserts have a steel back with a very thin layer of bearing material bonded to it. The bearing material is an alloy that can include metals such as tin, lead, aluminium and copper. Bearings designed for light duty may be made of white metal. It's an alloy of tin and lead with small amounts of copper and antimony. Alloys of tin and aluminium improve the load carrying capacity for intermediate applications. Copper-lead alloys give even more improvements. They're used in applications such as diesel engines and high-performance vehicles. Bearings need a difficult mix of properties. They must be hard enough to resist wear, but soft enough not to damage the shaft. The soft bearing surface also allows any hard abrasive particles to become embedded in the surface. They can become so deeply embedded, they're prevented from touching the rotating shaft by the film of oil. It's the mix of metals, tin, lead, copper and others, into an alloy that makes this combination of hardness and softness. In a main bearing, the upper half of the bearing fits into a machined section of a crankcase web. The lower half is carried in the bearing cap, which bolts onto the crankcase web. In a connecting rod bearing, its upper half is carried in the big end of the connecting rod. The lower half is in the connecting rod cap. One main bearing has thrust faces which accept the end movement of the crankshaft. These can be in the form of flanges that are part of the bearing. Alternatively, a separate thrust washer can be fitted into a machined recess in each side of the bearing cap. Sometimes a mating recess for each side is machined into the cylinder block and mating halves fitted to both. Under normal running conditions, spinning shafts ride on a microscopic wedge of oil. Oil flows through a long gallery in the cylinder block. Each main bearing has its own oil supply passageway from this gallery. Passageways drilled in the crankshaft carry oil from the main bearing journals to rod journals. Oil flow maintains the oil wedge between the shaft and bearing and carries away particles that could cause wear. Engine manufacturers specify the clearance required between the bearing material and the crankshaft. This clearance gives the best combination of oil pressure and flow. As clearance increases with wear, oil flow increases, causing oil pressure to drop. Then the shaft may rub against the bearing surface and wear even faster. This section examines the flywheel. A flywheel is a large rotating mass mounted on the rear of the crankshaft. On a car with manual transmission, the flywheel is very heavy, and its momentum helps smooth out engine operation. The flywheel links the crankshaft to the transmission through the clutch. The flywheel has a machined rear surface. It's the clutch's main driving member. Holes are drilled and tapped into the flywheel for attaching the clutch pressure plate. On a car with automatic transmission, the flywheel is usually called a drive or flex plate. The drive plate is lighter than a conventional flywheel because of the weight provided by the torque converter. The outer edge of the flywheel or drive plate has a gear called a ring gear. The electric starter pinion engages on this gear to rotate the engine for starting.